Hey, what's up, guys? This is Cheng here. So, today, let's take a look at today's daily challenge problem, number 377, combination sum number 4. Okay, so you're given like an array of distinct integers. So, notice these distinct integers and the target integer target, and it asks you to return the number of possible combinations that add up to the target, right? And the answer, okay, so the answer is guaranteed to fit in a 32-bit integer. Okay, so and for example, we have three numbers. Since the requirements this description is that all the numbers are distinct, right? That's why we have 1, 2, 3, and target is 4. But the output is 7. So why do we have 7? Basically, one numbers can be used multiple times, right? That's why we have the first one is 1, all 4 ones, right? And then we have 1, 1, 2, 1, 2, 1, 2, 1, 1, 1, 3, 3, 1, and 2, 2, right? As you guys can see, actually, so rather than combination, so this one is like more like a permutation, right? Because 1, 3, and 3, 1, they're counted as two distinct combinations, right? Cool. So and here are the constraints, right? And then there's a follow-up, right? So I mean, to solve this problem, since this one is like, since we can use this kind of numbers, as many times as we want, right? And then that's why to calculate the permutations, we can use like a DP solution, which in this case is like top-down DP, right? And for this kind of DP, the common approach is that we're gonna have like index, right? And then we have like a current values, right? Something like this. But for this problem, since we can reuse the numbers as many times as we want, so which means this index that doesn't make any sense, right? Because we cannot uh, use the index to only process the numbers after the index, because every time we can just use any of the numbers, right? And that's why to solve this problem, we can simply just use one the current value as the DP state. Basically, with the current value here, we're just trying to use any numbers here, right? With the current value, we try to use add any all the numbers one by one. Of course, we have to check, since all the numbers are positive, right? We need to check if the new current is not greater, it's not exceeding target. Then we just continue. Right, so we have a DP here, the DP, this current equals to what? Equals to the all the numbers, right? So we have a sum of the numbers, each number, right? And then plus sum of the of the DP, right? DP of the number, each number, right? Plus a current. That's going to be the total, the state transition function here. And why this transition function work, right? So first, we have to see if the state transition function can cover all the scenario, all the possible permutations. The answer is yes, right? Because every time we use each number, right, to update the current number. That's why we can guarantee to update to cover all the permutations, right? And second is that will we have like any duplicate uh, combinations, right? No, right? Because since each number at each of the DP state here, each number is distinct. So which means it doesn't really matter how many numbers we have added previously, but at the current state, we're gonna loop through each number, but because each number in the is different, that's why we have a number 1 here, right? Number 1, number 2, number 3, right? So because the current state, the current number, they're always different. That's why we'll never have like a duplicate combination, right? If we follow this state transition function here, and since every time we'll loop through the numbers here, it's guaranteeing that we'll cover all the possible combinations, right? And so this DP means that with the current total sum, right? What is what are the combinations, right? That can how many combinations in total that can give us the final answer, the final sum is target given the current one equals to this current. That's the definition of the DP, right? Okay, so I mean, to do the coding, when I'm going to use like a top-down DP here, that's why I'm going to use this kind of LRU cache, right? None here. And then, so in the end, I simply return the DP 0, right? So first, the exit condition is that when the current equals to target, we know we find like one combination. That's why we need to return return 1, right? Otherwise, we simply just loop through each number every time, right? In numbers, and we check if the current one plus the number is not exceeding the target, right? Because all the numbers are positive, right? And then we just simply do answer plus the DP of current plus number, right? That's how we accumulate the total numbers, right? For each of the number, because for each of the numbers, we're saying that okay, given like because the DP definition here, given the current total sum, how many combinations we can get, right? Given the current sum. Yep. So I believe that's it, right? If I run the code, did I? Oh, yeah, I forgot to return the answer in the end, right? Right. So, right, cool. So why is that? Because for the DP, given like a sum, right? Given like a sum, like a current as a current sum, the number of combinations, right? Given this kind of this current sum is fixed because at any state we can use each number, right? So that's why this DP state is fixed. That's why we can just simply break down this big problem into a sub problems, right? And that's how we come up with this DP solution, right? And yeah, so that's it, right? Oh, and the follow-up, right? So okay, so the follow-up is that if we allow negative numbers, so what changes we need to make here, and what limitations, and how that's change the problem, and what limitations we need to add to the question to allow the negative numbers. So if we have a negative number, so what does it mean? It means that this one will not work, right? Because we cannot simply check if the current one is greater, it's not exceeding the target, because the later one we may have like a bigger number in the end, or we may have like a negative number that can offset the current one. And another extreme case is like this. So if we have a negative 1 and 1, so if only these two numbers are in the numbers and the target is equal to 0, So as you guys can see, this one, it's going to be an infinite number of the combinations, because we can have infinite number of -1, 1, -1, 1, -1, 1, and so on and so forth, right? We can have like as many combinations as we want. That's why, if you allow the negative numbers, we need to add like a third parameter, which is the what? The longest, right? The longest length. The longest length of the combinations. And we'll use this longest length to stop, right? To stop our DP. Yeah, I think that's it for this problem. And yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.